So, welcome to today's live interactive session on geology and soil mechanics. So, in today's video, we will be continuing, or in today's lecture, we will be continuing the shear strength topic. So, we will be solving some more problems from shear strength, and we will be looking into the Skempton spore pressure parameter part. We will be solving some problems regarding those, and also we will be solving some problems from one or two problems from your vein shear part. Okay, apart from that, we will be solving our general shear strength problems related to triaxial test, which we solved in the last class. So with today's class, we will be actually ending the shear strength topic, and in the next 2 weeks we will be discussing mostly the mostly the retaining wall. Okay, the retaining wall topic, where retaining wall, where we will not actually retaining wall, not we will be dealing with the earth pressure. Okay, the earth pressure topic which generally acts in a retaining wall. So we will be dealing with the topic of earth pressure, or passive and active earth pressure, and then we will be solving those problems in the upcoming 2 weeks. And in the last week we will be summarizing all the topics from the start to end. Everything we will be solving some problems uh, from the beginning to the end, so that we can recapitulate, or we can recall whatever was taught in this course in these 12 weeks. All right, let us start today's session. So in the previous class, actually we had discussed about this uh, test, triaxial test. Those were my CD test. It is the consolidated drain test, the consolidated undrained test, and my unconsolidated undrained test. Right. So these three tests actually we had discussed. So now in this class also we will be revising once those tests, whatever we had learned in the previous class. So first we have our CD test. So as we had discussed in CD test actually, so in all triaxial tests there are two stages, as we know. The first stage is the consolidation state, and the second stage is my shearing stage. Okay, first is the consolidation stage and the second is my shearing stage. So in CD test, in the first stage, what we will be doing, as it is a consolidated drain test, so in the first stage my drainage valve will be open. We will be applying our cell pressure. Okay, we'll be applying the all-round cell pressure, which will be resulting in a minor principal test sigma 3, which will be developing all around the sample, and we will allow our soil to actually consolidate. Okay, consolidate under the cell pressure. So this process of consolidation is actually very slow, as you all know, because my pore water takes a large amount of time to drain out. Okay, drain out. So this process of consolidation is very slow, mainly for clays especially, it's very slow. So in CD test, first we have to consolidate the soil, and after the process of consolidation is over, what we do is that we apply the deviator stress. Okay, so by applying the deviator stress, or the extra axial stress, what happens is my sample starts shearing, and after that, as we start keep on shearing, as it is a drain test, volume changes will be there. So during the shearing, the rate of shearing, or the rate of shearing is kept very slow. Okay, the rate of shearing is kept very slow, so that the water actually takes time, right? The water actually can come out. Okay, come out, and in that, while coming out, it doesn't actually increase the pore water pressure. So the main reason that this drain stage is very slow is because shearing is done very slow, so that extra pore water pressure actually doesn't develop. The water is able to completely drain out slowly, and we are allowing actually the water to drain out so that there is no development of pore water pressure. Okay, so this 3D test actually takes a large amount of time. Okay, so if we don't have time, so generally it's CU test, you can go for CU test. Okay, though the in CU test, as you know, you can obtain both the total stress and the effective stress parameters, but in CD test, as the pore water pressures will be zero, obviously, because we are allowing drainage. So the result whatever we get, that is our nothing but the effective parameters. Okay, so from CD test we get the effective stress parameters. Now before we start the consolidation process, in the first stage we must actually make sure that my soil is completely saturated. Okay, so my soil should be completely saturated. In general cases, we should ensure that our soil is completely saturated. So how can we test that my soil is consolidated? So we can test by determining the Skempton pore pressure parameter B. So you can see B is nothing but the ratio between the ratio between the pore pressure developed due to the application of my all-round stress divided by the sigma 3 is nothing but my all-round stress. So this is a cell pressure that you are applying in the first stage. So if that ratio is actually equal to 1, close to approximately equal to 1, so in practical in real life scenarios, we do not get approximately equal to 1, so we do not get exactly equal to 1. So if the sample is around 0.95 0.95 around like that, so we say that the soil is completely saturated. So in the real life there are some errors of the instrument, like instrumentation error or some other factors. So we say that if it's close to 0.95, we say that it's almost saturated. 0.95, 0.96, 0.97, 0.98 like that, close to 1, we say that our soil is completely saturated. Now, so as you know, if the soil is completely saturated, whatever cell pressure we will be applying, that increase in cell pressure will be taken by the what? Taken by my pore water, right? So that's why my pore pressure will increase. Correct. So whatever you are applying, say you are applying 2 kPa of cell pressure, increasing, so delta sigma 3 is my 2 kPa. So my increasing pore pressure should also be 2 kPa, because my soil is completely saturated. So this way you can calculate B will be equal to actually change in the pore pressure divided by change in the cell pressure, right? So if those are equal, we can say that my soil is completely saturated, right? So we have to calculate in the while before beginning our test, we have to actually check in our instrument, while we check in our device, that our pore pressure, this B, that is why UC by sigma 3 ratio is actually coming to 1, equal to 1. So if it's 1, we can say that the soil is completely saturated, and then we can begin our consolidation stage by opening my drainage valve. Okay. So you might be wondering, how do we actually consolidate, not consolidate, how do we actually uh, what to say, how do we actually saturate the sample, right? So there is a process of saturating the sample. Okay, so in these years, several years, many researchers have done many experiments, and they have given some uh, process where we can saturate the sample very fast. So what we do is that we apply back pressure and cell pressure simultaneously, and using that actually we saturate the sample. Okay, also we need to put some filter paper around that sample, so that the soil gets saturated. There is a procedure which you can find in the literature. So there is a defined procedure using which what we do, we saturate the sample. And how do we check that our soil is completely saturated or not? We check it by calculating our V parameter, and our V parameter should be close to 1 to ensure that our soil is completely saturated. Okay, so after we ensure our soil is completely saturated, what we do is that we start our consolidation state. How do we start our consolidation state? we keep on increasing the cell pressure, and whatever in that and we fix it to 1 point, right? We increase and then we fix the cell pressure to 1 point, and then what we do, you open the drainage valve. As soon as you open the drainage valve, what will happen? The pore water will get coming out. Okay, it will start to come out. Okay, as this pore water actually starts to get expelled, my pore water pressure will increase and my effective stress will increase. With all these things we learned in our consolidation stage. So our consolidation will begin. So like this, what we need to do, we need to completely see that the pore pressures are all absolutely equal to 0, that which will mean that my consolidation state is ended. Okay, so after this consolidation stage, what we do is that we start applying the deviator stress. Okay, so we start applying the deviator stress, and then we keep on increasing to some extent, and after that we will see that the soil has failed, right? So that point will actually give my failure deviator stress, right? So for say sigma 3 1, you will get some value of deviator stress like that. Like this, you will be getting some deviator sigma 3 and deviator stress value. So we will get my sigma 1 from there, is this plus this will give my sigma 1 and 1, like this here also we will get. So after we get, what we need to do, we will plot it. So you will get one circle like this, and again. Okay, then what we do, we draw the common tangent to this circle. Okay, so this will be actually my failure envelope, and this angle will be actually my phi dash. This C you obtain will be C dash. Okay, this will be the effective parameters. Why effective parameters? Because my pore water pressure is 0. Okay, now in the CU test in the first stage, is exactly same as the CD test. Okay, so there is consolidation. So after the consolidation is over, what we do, we close the drainage valve. Okay, close the drainage valve, and after closing the drainage valve, we apply our deviator stress. So here we are not allowing drainage to occur. So as we are not allowing drainage of water to occur, what will happen? As we are applying the deviator stress, as we are increasing the deviator stress, my pore water pressure will be generated, right? Pore water pressure will be generated, and pore water pressure will keep on increasing as soon as we start applying this deviator stress, right? So here we define another pore pressure parameter, which is a, here we have written as A bar. A bar is nothing but the ratio of the change in my increasing pore pressure due to the increasing deviator stress. Okay, so pore water pressure increased by this amount or increasing the deviator stress by this amount in the second stage. Okay, so as I was saying, why CU test is sometimes prefer CD test? Because in CU test is actually faster. Here in the second part, the second stage, we need not bother about applying the, did not bother about the drainage of water. So that second stage, the undrained part in the second, in the CU state, in the CU test, that can actually be completed fast, very fast, right? So CD test is actually very long. So if you want to expedite the process, we can do the CU test, right? Though there might be some changes in the values of the CN5 value that we calculate, but it depends upon the engineer to choose the CN5 values. Okay, so we can do the CU test. So in CU test, we will get both we will get both the total stress parameters, also the effective stress parameters, right? So these are nothing but the total stress parameter minus the pore water pressures. Okay, so we can get both the total stress circles and the both the effective stress circles. So we can get both the envelopes, right? So if you plot say if this is our total stress circles, then our effective stress envelope value is something like that. Okay, something like that. This is phi dash. Okay, so phi dash is always greater than phi. Okay, generally, right? So we'll be getting this. Now we see that at failure, my a value, a bar value, it is at failure. F, we are writing F for at failure is nothing but ud at failure by sigma d at failure. Okay, failure. So for a normally consolidated clay, my a value is a value generally varies from 0.5 to 1, and for over consolidated clay it varies from minus 0.5 to 0. Why minus? Because if you recall, if you do not allow drainage in case of over consolidated clay, what will happen is that, say, okay, so what will happen is the pore pressure actually will behave like this. Okay, this is, say, this is my stream, this is over consolidated, so positive direction, negative direction, this is 0. So as you keep on sharing, what will happen in case of this, see, this part actually is my normally consolidated part. In the normally consolidated part, what happens? My pore water pressures are always positive, and in over consolidated soils, there is a, or in over consolidated clay or in dense sands, there is a tendency that if drainage is not allowed, then the negative pore water pressure activity develops. So due to this development of negative pore water pressure, we are actually getting this negative AFL. Okay, you are getting this negative A value from here. And if the soil if the soil is normally consolidated, my pore water pressures are always positive, right? Pore water pressures are always positive. So that's why we have this A value varying from 0.5 to 1. Okay, so these are the differences. So for normally consolidated or loose sand, normally consolidated clay or loose sand, or consolidated clay or dense sand, the behavior is kind of similar. Okay, so this is because, say, you are allowing drainage, then the normally consolidated clay actually the volume tends to increase. You allow drainage, and for over consolidated clay there is a tendency for the volume to increase. So there is a tendency of dilation. Okay, so that's why this happens. And now we have the UU test. So UU test, the first stage also we are not allowing any consolidation. So what we do, as soon as we saturate the soil, right, we do not allow any consolidation. My drainage valve is closed, so we raise the sigma 3 to a certain cell pressure to a certain amount, and then what we do, we start increasing our deviator stress. Okay, so we are not allowing drainage in both the stages here in UU test. So it is a very fast test. Okay, so you can see the total increase in the pore pressure is nothing but U is equal to UC plus sigma delta UD. So this UC is coming from my application of sigma 3, and my delta UD is coming from my application of delta sigma. This is my increasing deviator stress. Okay, so UC is due to the application of sigma 3 and UD is from the application of sigma t. Okay, so what is UC? You already said UC is nothing but B into sigma 3. And what is delta sigma UD? It is A bar into delta sigma D, right? So totally will be B into sigma 3 plus A bar delta sigma D is nothing but this, right? So sigma D is nothing but sigma 1 minus sigma 3, right? So we're getting this. And in UU test, if you remember, we are getting circles of same diameter, right? We are getting envelope like this. Why are we getting like this? Because the soil is completely saturated. We are not also in the next second stage. We are not allowing any drainage. Like the first stage also not drainage, second stage also not drainage, right? What happens? Whatever extra sigma 3. So for 1 sigma 3, sigma 3 1, you are getting sigma d1 is the failure. Okay. For sigma 3 2, you are getting sigma d2. So in this case, what happens? These two are actually equal because the soil is actually failing at the same point, because whatever extra load you are applying, that actually develops, that is actually taken by my pore water and not the soil skeleton, right? The soil skeleton is actually not taking my load. The actual load is actually extra load stress that you are applying. It is being taken by the pore water. That's why my soil actually fails at the same diameter stress. So we are getting circles of same diameter, and from U test you always get phi equal to 0, right? So now you one more test we had studied, that was my UCS test, right? UCS, unconfined compressive strength test. So in unconfined compressive strength, what happens? You are just keeping the sample and you are applying an axial stress, axial load. So in UCS test, my sigma c or my sigma 3 is actually 0, right? There is no confining stress. So if I want to draw the Mohr circle of my UCS test, it should be something like this, because my sigma 3 is 0, right? And this is nothing but my UCS value, right? Now if I want to find out my C value, that is the cohesion value, okay, this is my cohesion value, right? This is the cohesion will be nothing but, if this is my UCS, say QU, this will be nothing but QU by 2, this much, nothing but QU by 2, okay. Okay, so in UCS test you will be getting a circle something like this, right? So sigma 3 is 0, it's following, which is nothing but my QU, okay. And this, this gives my C value, cohesion value, undrained cohesion value, right? So how much is this length? This length is nothing but QU by 2. Now what is my shear strength? C plus sigma 10 phi. So from here, see, my phi is 0, so it's nothing but C, nothing but QU by 2. Okay, so generally, see, theoretically, whatever C value you calculate from UCS test should be equal to the UCS value that you calculate. You should be equal to the C cohesion value that you calculate from the UU test. Okay, theoretically this should be the case actually. Okay, so the next topic that was introduced in the previous in the this 9th week lecture was our stress path. So what is stress path actually? Okay, the stress path is nothing but the locus of the points representing the stress states during the progress of the test. Okay, so while we are doing the test, say take for example any triaxial, say take for example a triaxial test. Okay, so for simplicity we can even take my UCS test. So in UCS test, what you are doing, you keep the simple and just you keep on applying my axial stress, axial load. Okay, so you're increasing the axial load, say first year 1 2 3, like 3 kPa 4 kPa, like this you are increasing the axial load, right? So at certain point it gets failed. So this progress of the test, right, there is a progress of the test, you are gradually increasing your applied stress. So that gradual increase in applied stress is actually represented in terms of my stress path. Okay, that is actually represented in terms of a stress path. That's why you are saying it is the locus of the points representing the stress states during the progress of a test. So by seeing a stress path, we can actually guess, we can actually tell what kind of test has been conducted on that soil. Okay, so for this stress path, we use this q dash p dash plot. We generally use this. So this q dash and p dash represent nothing but my the top coordinates. So this is, say, this is my mode circle, right? So you're doing your test, right? So you are gradually increasing your sigma d, so sigma 1 is increasing like this, and at a certain point it fails. Certain point, this is the failure sigma 1 below. So this is the progress of the test. So this actually represents the top coordinate of these mode circles. Okay, this top coordinate of the mode circle. So if this one is sigma 3, this is sigma 1. So this x value is sigma 1 plus sigma 3 by 2. And what is this y value? Sigma 1 minus sigma 3 by 2. So the coordinate of this point is nothing but my p dash and q dash, or p comma q. So p dash in terms of the effective parameters, and p and q in terms of the total stress parameters. Okay, so now let us take the example of my CD test. So for normally consolidated clay in stage 1, my derivative stress is 0 because we are just consolidating the sample, right? So sigma 3 dash equal to sigma 1 dash equal to sigma 3. Isotropically consolidated means, see, consolidation. So here what is isotropically consolidated? So actually their consolidation also might be anisotropy. Say during the consolidation stage what you are doing, generally what you do, you apply same this sigma 3 all round, right? Sigma c or sigma 3 all round. So anisotropic consolidation means, say you apply in axial this direction you apply sigma c1, and this direction you apply sigma c2. So these are known as anisotropically consolidated. And isotropically consolidated means all around you are applying the same stress. That is a general case. That is our general case. It is nothing but our general case. Okay, during the consolidation process. Right. So for normally consolidated clay in the first stage, my sigma d is 0, and isotropic consolidated, so everything is equal to sigma 3. So what will be p dash? P dash will be nothing but sigma 3 dash plus sigma 3 dash by 2, so it will be nothing but sigma 3 dash equal to sigma 3. So sigma dash are equal to the total because my pore water pressures are equal to 0. Yeah, no pore water pressure, so sigma dash is equal to sigma. And what is it will be equal to q? Q will be nothing but 0. Right, so this is represented by my point I, this point. Now at some other time, okay, here's the test progresses. Say at time t equal to 0, say at time t1, okay, t equal to 0 we have this, and at this I point, and that as the test progresses, we are applying, now we are going to the second stage. The second stage, what we are doing, we are applying derivative stress. What will be sigma 3 dash will be sigma 1 dash will be sigma 3 dash plus this delta sigma d, right? And there are no pore water pressure, so sigma 3 dash is equal to my sigma 3, right? Because the pore water pressure is 0. So this will be my p, this will be my q. So our test progresses to this stage now, d dash. Okay, like this what will happen, we will keep on doing the test, and this point, this sigma 1 is nothing but my failure sigma 1. Okay, this sigma 1 is nothing but the failure mode circle. This is my mode circle at failure. Okay, so if we join all these points, all these p and q points, we will get one straight line. Okay, that this straight line, this I T line, is nothing but my stress path. Okay, so and this stress path is actually inclined at 45 degree to my this p axis. Okay, now this is my p or p dash, q or q dash. So for consolidated drain test, both p and q are same always. The p and p dash are same, q and q dash are same. So we will be getting a straight line inclined at 45 degree. This is my high point. Okay. Right. Now if you want to draw also, if you draw the more circles also in the same plot, you want to in the sigma and the tau coordinates, if you draw in the same plot, then you can draw the more circles also, right? So this will be my more circles. These will be my more circles. Now if we join this O point, okay, if you join my O point with D point, this is nothing but my failure envelope in my, this is the modified failure envelope. Okay, if you join this O and my D line, this is actually extended till F dash. So this O F dash line is nothing, is called the modified failure envelope, is nothing but my KF line. Okay, and what was my original gen? This OF line is nothing but my failure envelope that you will get. How will you get this failure envelope? So this failure envelope you will be actually getting by joining, you will be drawing various more circles for various tests, various values of sigma 3, and joining the tangent. This will give you your failure envelope. Okay, and how will you actually get your this modified failure envelope? If you join all these lines, the lines where uh, this next point, okay, this point, coordinate of this, if you join all these points, you will get your modified failure envelope. Okay, the modified failure envelope is actually inclined at alpha angle, and my failure envelope is inclined at phi dash angle, as you all know, right? So now if you want to get some relation between this phi and alpha, what we can just see at the geometry. Okay, from the geometry we get that my q dash, this phi dash is nothing but sine inverse of this tan phi. Okay, this phi inverse of tan phi. So if you know the kf line, from the kf line we can actually get our phi values. Okay, so say you have sigma 1 and sigma 3 values at failure. Okay, you have sigma 1 and sigma 3 values at failure. From these values you can get this d point, right? You can get p point, you can get q point, right? So what you can do is that you can plot your modified failure envelope. Okay, from there you can measure your alpha, and from alpha you will get the phi value. Again, if you want to check this, what you can do is that you can use these values to draw your more circle. So for different, you will get different values, right? For different sigma 3 you will get different sigma 1 at failure. So like this, if you draw this, from here you measure the phi value, then you can check whether this relation holds true or not. Okay, so this, why do you use this PQ line? So generally what happens is that this drawing circles is little bit difficult, right? You have to draw circle. Drawing of circles is little bit difficult. So if you, so and drawing a straight line is relatively easy. You just need some points and you join, you will get a straight line, right? So drawing circles is difficult. So after drawing circles and then drawing tangent, this thing is a little bit difficult. So what we can do is that we can directly draw my this modified failure envelope. We can directly draw my modified failure envelope, and from the modified failure envelope, what we can do, we can find out our C and phi values. Okay. Now we see the example of the CU test. So in CU test, the first stage is same. First stage there is no sigma 3, right? So all these are equal, and there is no pore water pressure, so it will be nothing but the same, this I point. Okay, I point. In the second stage, as it is a under test, what will happen is that you will be getting uh, some pore water pressure values. Some pore water pressure values will be generated while we apply this your deviatric stress. So from there, if you plot, you will get a stress path actually like this. Okay, this is my modified failure envelope or KF line. Okay, so this line IU, this is nothing but my not a straight line, it is actually a curved line. Okay, so it is actually a curved line. And if you want to draw the total stress parameters, C, P dash and Q dash. Now if you want to draw P and Q, you will actually get a line like this. Okay, and say you have like this. Okay, and this is for two tests you are doing. So you have, if say you have this figure in front of you. Okay, so someone asks you to identify uh, what are the tests that were conducted. Okay, so you can directly say that this is for the CD test and this is for my CV test. Okay, just by looking at my Q dash P dash plot, you can directly say this, right? So this you can directly say that just by looking at the P dash Q dash plot, you can see that this is the line for my CD test and this is for my CV test. Okay, they are originating from the same point, because in both these tests what we are doing is that we are uh, consolidating the soil up to a same value of my cell pressure. That's why they are here, the point is same. So this stress path is actually very important in critical state solid mechanics. So critical state soil mechanics is actually advanced topic. Okay, it's a postgraduate level topic where the various what to say the various soil models are actually described with the help of this uh, stress paths drawn in the PQ space. Okay, so that's why we need to understand this stress path, because in this critical state soil mechanics, this forms a very this is a very helpful tool for us to represent the various soil models and how to understand how the soil actually behaves. Okay, so this is a critical state soil mechanics actually advanced level course. Okay, it's generally taught in postgraduate level. Now see, we had studied about our pore pressure parameters A and B, right? We have seen that how this A and B and what are the approximate values that actually we should have for normally consolidated or consolidated clay, for completely saturated soil, what is the value we should get a value of B close to 1, and for normally consolidated clay, what is the value should be of A between 0.5 and 1, for a body consolidated should be minus 0.5 to 0. So all these things we understood, right? We saw this in the previous slides. Now from basics of soil mechanics, see, so these A and B parameters were actually derived by Scampton from the basics of soil mechanics, right? So this was completely discussed in the theory class. So still I will just go through a bit so that you can recapitulate. So this equation actually we had derived. Okay, this was derived to us, where change in volume into 3 by the sum of the all the increasing stresses in all the three directions is nothing but a constant. Okay, this is nothing but a constant, which is called the compressibility of the soil skeleton, right? So this is a constant for a particular amount of soil, particular kind of soil, because it depends on E and my Poisson's ratio. E is nothing but the Young's modulus of soil, and this mu is nothing but the Poisson's ratio. So this is constant for a particular kind of soil. So from here you can write delta V, just by rearranging you can write this, right? Now this delta V, this is the change in volume, total change in volume of the soil sample is nothing but equal to, you can write it, that is equal to the change in volume of the pore space. Okay, the volume of the pores will change, that will be reflected in terms of the change in total volume of the soil, right? So the change in volume is nothing but equal to the change in volume in the pore space. The changing volume of the pore space, we are writing it as NVCW delta U, right? So porosity into volume, this is nothing but the volume of the pores. Volume of the pores into CW. CW is nothing but the compressibility of the pore. What is pore fluid? Fluid might be air, might be water. Okay. CW is the compressibility of the pore fluid and delta U is the pore water pressure. Right. Now we put this here. Okay. Then we equate these two. We get this as the expression for my increasing pore water pressure. Okay. Increasing pore water pressure. So what is by increasing pore water pressure is 1 by 1 plus L CW by CV into this value. Okay. Now for how we are getting, so this sigma 2 is actually equal to sigma 3, right? The sigma 2 is actually equal to sigma 3, so you can write this expression, or from here you can write, or delta U is equal to B into this. So we had seen this expression before only. Okay, so we had seen this expression before. So this U1 part, so this part you are writing it as delta U1. Delta U1 is nothing but B into sigma 3. So the increase in pore pressure that is contributed during the application of my cell pressure. Okay, that is this delta U1. And what is my delta U2? Delta U2 is nothing but the increasing pore pressure due to the increase in my deviatoric stress. Right. So you are getting this. So one more thing you can see here, this A dash is equal to A into B. Okay, this AB is together written as A dash. Okay, and for saturated, if the soil is completely saturated, then B is equal to 1 for saturated soil, then you will get A dash equal to A. So for completely saturated soil, the pores will be completely filled by water. So in the pores there will be completely water in it, water in the pores. So as there is water in the pores, my CW is much lesser than CV. Right, CW is much lesser than CB because we are considering the soil is incompressible. Sorry, the water is incompressible. So CW will be much lesser than the CB thing. Don't confuse this CB with the coefficient of consolidation. Okay, that is a different, and this CB is different. So this is much lesser than CB. So this ratio will be equal to 1. So my B will be equal to 1. Okay, so this ratio will be close to 0 because this is very less, this is very high. So my B will be close to 1. And for dry soil, so my pore is completely filled with air, so the compressibility is very high for air, right? Air is a gas, so compressibility is very high. So this CW by CV, this is very will be close to infinity, so my B will be equal to 0. So how can we measure B? We already studied that B can be measured in the UU test in the first stage only. So completely saturated soil, you are applying you are increasing say your cell pressure from 1 kPa to 2 kPa. Your pore water pressure also should increase from 1 kPa to 2 kPa, or whatever, say it should increase by 1. Okay, so the increase in your applied cell pressure should be reflected in terms of the increase in the pore water pressure. Okay, if that is exactly equal to 1, you are saying that my soil is completely saturated. Okay, so this thing we already discussed. And how can we measure this A dash parameter? This can be measured in the second stage in the CU test. So you are applying some deviatory stress, and due to that application of deviatory stress, your your pore water pressure is increasing. Right, to increase in applying application of the deviatory stress, your pore water pressure is increasing. So the ratio of these two will give you your A dash. And you know, if the soil is completely saturated, my A dash is equal to A, or completely saturated, my A dash is equal to A, right? So we are getting A equal to A dash equal to delta U by sigma 1 minus sigma 3. Okay, and as it is the CU test, in the CU test whatever pore pressure is generated, so my delta U was delta U1 plus delta U2. So this delta U1 is due to the increase in the cell pressure, whatever pore water pressure is generated. But in CU test, there is no development of pore pressure in the first stage because we are allowing drainage. So this is 0. The U will be nothing but my delta U. So we are writing this here. Okay. Now let us start solving the problems by one. So this is this shear strength is actually very conceptual, right? It's very conceptual, and uh, if someone is studying like for any geotechnical engineer, right? Geotechnical engineer, this these basics of soil, the shear strength should be very strong because shear strength forms the main structure of soil mechanics. Everything depends on the shear strength. Okay, so this whole mechanics of how soil behaves is actually dependent on the this all these things. So in reality, the shear strength chapter is very vast. In this course, just like you have been introduced to the basics. So the shear strength chapter, we can go into more depth. This chapter, we can go into this critical soil mechanics and many more things. Many more things are the main. This soil theory is plastic. Then we can go to the uh, how soil behaves in plastic state. All these things we can uh, go. All these things are ultimately dependent upon this shear basics of this shear strength. Okay. So let us now go to the problems. So the first problem we can see an UCS test was conducted on a soft clay in both in situ and remolded samples. Okay, so we have both in situ sampled and both remolded sample. So if you recall, what are in situ and remolded sample? So in situ sample is nothing but directly like using some say apparatus. What you are doing, we are taking out the soil from the ground, but keeping in mind that the soil structure or the arrangement of that soil is not hampered in any way. Okay, that is called the in situ sample. A remolded sample means you have taken soil from there, soil from a site, and then you have remolded it, like you have the soil, just loose soil was there available, and what you did using uh, 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 the sample cutter and all those things, what you did, you form the sample again at the particular water content, void ratio that was present in the soil. So you are actually manufacturing that sample in the lab using that soil. Okay, using the so that is actually the remolded sample. Yeah. So we have the in situ sample and we have some remolded sample. Okay, so in situ sample is nothing but what? Undisturbed sample. A remolded sample is a disturbed sample. You are remolding the soil again in the lab. Okay, so lengths are given, lengths are same, initial area is same, extension of spring at failure is given, spring constant is given, and axial deformation is given. So we need to determine the UCS, the uncomforted conversion strength of the soil in both conditions, that is the in situ and the remolded sample. And also you need to determine the sensitivity of the soil. Right. So can you recall what is sensitivity? What is sensitivity? Sensitivity is a ratio, right? So what is sensitivity? What ratio is?
In situ shear strength divided by remolded shear strength.
Yes. So undisturbed strength divided by the remolded strength. That is my sensitivity. So we can so my remolded you will see that the UCS of my remolded sample will actually becoming lesser than that of the in situ sample. Okay, so now let us calculate the failure load. Okay, so failure load, let's calculate. So 20 mm, so 20 into 15, 300 Newton in case of in situ, and in the other case it's 15 to 15 25 Newton. It is remolded sample. Okay, so these are my failure loads. Okay, now in situ, for the in situ sample failure load we have calculated how much? 300 Newton. Okay, we have calculated 300 Newton as my failure load. Now what we need to do is that we have the failure load, just we need to divide it by area to get the UCS value, right? So the area, can we directly use this area, initial area? No, right? Because during the test the area keeps on changing due to the straining, right? So we need to calculate the changed area. So final area will be nothing but N01 plus string. So what is N0? 1500 meters square will be mm square. Okay, 1500 divided by 1 minus yield strain is given 9 mm, right? So this is del L by L. 1 del L is 9, and what is the length? Axial deformation is, what is the length? 150 by 150. So please calculate how much AF is coming. It will be 1595.75 mm square. Okay, so what is my Q? 300 5, it will come out as 0.188 in situ, and then we have my remolded. But my failure load was 225 newtons. Final area will be 1500 by 1 minus 20 by 150. It will be 14993 square. So you are seeing my remolded strength is coming lesser than in situ strength. So what is my sensitivity? QU undisturbed by QU remolded, right? So undisturbed is 0.188, 1.25. Okay, so this sensitivity actually falls between 1 and 2. So this is actually a low sensitivity soil. Okay, this is actually a low sensitivity soil. All right, so pretty straightforward question. Now let us go to the next question. Okay, a vein 100 mm in dia and 200 mm in height was pressed into soft clay in a borehole. The torque was applied and gradually increased to 100 Newton meter when failure took place. We need to determine the undrained shear strength. Okay, so it is a problem of our vein shear test. So in vein shear test, the vein is inserted into the soil and it's rotated, right? So that there is a torque applied in the vein, okay, and the vein is rotated. So that torque is actually related to my undrained shear strength, right? So why are you calling it undrained shear strength? Because the soil test is fast, very fast, right? We do not allow the poor water pressures that get developed during the application of the torque to get dissipated. So we call it a undrained test. Undrained, we can always get the undrained shear strength. So the dimensions of the vein are given, and also the failure torque is given, right? So dimensions of the vein are given by failure. So let us write all these things. So D is 100 mm, H is now my undrained shear strength. Undrained is equal to torque by 6. So if we consider uniform distribution at the top and the bottom of the veins, then we will get this relation, okay, for the undrained shear strength. So beta value we are considering for the uniform, that's why we are getting this expression. Now what is my T? 100. So please calculate this. Please calculate. Let's see. So these vein shear tests are generally used in this very highly sensitive clays. Okay, uh, in say in you have clay near the shoreline or something like that. Those things that are the same. It is very difficult to collect undisturbed sample. So when it is very difficult to collect undisturbed sample, this wind shear test is very helpful to us. Okay, so you can take in. There are two kinds of wind shear test actually, laboratory and my field. So at that time, you have to resort to a field wind shear test to determine the shear strength of the soil, because collection of that undisturbed soil sample is very difficult in those cases. So please calculate this one. So this is coming as 0.02 per square. So it's very less, 2.73, you can say kPa, very less. Okay. Okay. So in an in situ vein shear test on a saturated clay, a torque of 43 Newton meter was required to shear the soil. The dia of the vein was 50 mm and length was 100 mm. Determine the undrained shear strength. The vein was rotated rapidly to cause remolding of the soil. The torque required to shear the soil in remolded state was 8 Newton meter. Determine the sensitivity of the clay. Okay. So here it's same. It's similar to the previous problem. So we need to determine in two cases, for the in situ sample and the remolded sample. And then we need to determine the sensitivity. Okay. So let us first calculate for the in situ. It's better to write here remolded. Sorry. Understood. Same. So what is my T? T3 Newton meter. So I convert it to convert it to Newton mm, then pi into, see, to calculate this one, and similarly for remolded we will have, so please calculate these two. So this one will be, this one will be 0. Okay, now we need to determine the sensitivity. The sensitivity is nothing but 0.0713 delta 5.2. Okay, so it is a sensitive soil. Okay, I hope this was clear. So very straightforward, direct. You need to use the expression relating our shear strength to the torque, and directly you can find this out. Okay. Okay. So an embankment 5 meter high is made up of soil whose effective stress parameters are C dash equal to 50 kPa and phi dash equal to 16 degrees, and also gamma is 16.2 kilonewton per meter cube. The pore pressure parameters as found from the triaxial tests are A is equal to 0.4 and B is equal to 0.49. Okay. Find shear strength of the soil at the base of the embankment just after the soil has been raised from 5 meter to 8 meter. Assume that the dissipation of pore pressure during the stage of construction is negligible and that the lateral pressure at any point is 1/2 of the vertical pressure. Okay. So we have a 5 meter high embankment for which C dash and phi dash values are given to us, and also we have the pore pressure parameters for that soil that were found from a triaxial test. Okay, those are given as A is equal to 0.4 and B is equal to 0.49. Now we need to find out the shear strength at the base of the embankment. Okay, just after the soil has been raised from 5 meter to embankment. So initially the embankment height of the embankment was 5 meters, then the height of the embankment has been raised to 8 meters. Okay, so we need to find the shear strength of the soil at the base of the embankment during this, after this process. Also there is an assumption that has been given, that assume that the dissipation of pore pressure during the stage of construction is negligible. Okay, so undrained condition, right? So there is no dissipation of pore water pressure that is being is there during the construction from while the embankment is being raised from 5 meter to 8 meter. During this construction phase, there will be pore water pressures that will be get developed. So this pore water pressure does not get dissipated. Okay, there is no dissipation of this extra pore water pressure that gets developed in the construction. Also the lateral pressure at any point, there is a, say, vertical pressure you can find out, right? So the lateral pressure is equal to the half of the vertical pressure. Okay, it is being given. Now can you tell, is the soils completely saturated? Can you tell me, is the soil completely saturated or not? or the soil is partially saturated. This embankment is the embankment soil completely saturated, or is it not saturated, completely saturated? This is the question.
Not completely saturated
Why not completely saturated?
because B is not equal to 1.
Yeah, as B is not even close to 1, thus that soil is not completely saturated. Okay, so now let us try to first. So we have been asked to calculate the shear strength. So to calculate the shear strength, what do you need? You need C value and my no C. What is my shear strength? My shear strength is, this is my shear strength, right? So this C dash value is given to us. I need to calculate this sigma dash value. Okay, this sigma dash value I need to calculate, and this phi dash is also given to me. So the main task is to calculate the sigma dash value. Now how can we calculate the sigma dash value? So in order to calculate the sigma dash, this is the effective normal stress, we actually first need to calculate the pore water pressure. Okay, so actually need to calculate the pore water pressure that gets developed during the construction. That increasing pore water pressure, that we actually need to find out to calculate this effective stress. Okay, so what is my delta U? This, right? So this is my expression for the increase in pore water pressure. First tell me what is delta sigma 1. Delta sigma 1 is nothing but the increase in vertical stress. So during the construction from 5 meter to 8 meter, when the height of the embankment is raised, so what is the increasing vertical stress? Please tell me. Due to the construction, my height of the embankment is raised from 5 meter to 8 meter. Okay, so due to this increase, there is an increasing vertical stress, right, at the bottom of the embankment. So here we had the embankment, then it was raised. Okay, initially it is 5 meter, now it's 8 meter. So here the vertical stress will obviously get increased, right? So can you please tell me what is the increase in vertical stress due to this construction?
Gamma into 3 meter.
Yeah, gamma into 3 meter. So 3 into 16.2 is uh, yeah, 3 into 16.2, it is calculated 16.2 into 3, 48.6. Okay, so this is my increase. Now can you tell me what is the increase in my lateral stress? It is delta sigma 3. What is the increasing lateral stress? It's already given in the question.
Here we are not considering effective stress, means pore water pressure we are not deducting.
No, first we will you need, no, we are not deducting. We need to find out the pore water pressure. Okay, we are calculating the pore water pressure due to the increase in these stresses. We do not know the U value, right? So we cannot calculate this sigma 1 dash, sigma 3 dash. We do not know. How can we calculate? We do not know the pore water pressure, right?
Okay.
So we first, so that is our first target. That our first target is to determine the increase in the pore water pressure due to this change in stresses. So this delta sigma 3 is given in the question already. Here you can see, well, 24.3 kp. Okay, we got this. Now let us calculate the delta U. This delta U. Delta U is equal to B. B is 0.49 into 24.3 plus 0.4. It is A. 48 point how much? 48.6 minus 24.3. Okay, so please calculate delta U. 0.49 into 24.3 plus 0.4 into 48.6 minus 24.3. It will be 16.67 kPa. So due to this construction, my pore water pressure is actually increasing by this amount, 16.67 kPa. Okay. Now tell me my sigma n. It is the vertical or normal. There is the vertical or the vertical normal stress acting here. It will be nothing but 8 meter into gamma. Okay, which is 8 into 16 point how much? 16.2. Okay, and what will be sigma dash? Will be 8 into 16.2 minus 16.67. Okay, so this will be 8 into 16.2 16.67, which is 112.93 kPa. Okay, now we just got the effective parameters. Okay, now you can calculate the shear strength. So what is the C dash that is given to me? 50. Sigma dash, you know, 112.93 10 16 degrees. So let's calculate 50 plus 112.93 into 10 16. It will be 82.38 kPa. Okay, so this is my shear strength. Okay, so let us see what do you how do you calculate. So first step was to calculate the increase in my pore water pressure. So increasing vertical stress, I know this is my increasing vertical stress, that I am calling as sigma 1. Increasing lateral stress, this value is given half of delta sigma 1, that I am putting this in this my u equation, then I am getting the increasing my pore water pressure. Right, then as I have got this pore water pressure, I just deduct this from my vertical stress. I'll get the effective value, and then I can put all the values in the equation to get my shear strength. Okay, okay, so this is the next problem. Problem 5. A saturated clay sample was obtained from the field without allowing the water content and the void ratio to change. That is undisturbed sample. Okay, we are not allowing the water content and the void ratio to change. A sample was subjected to the following stresses in the field. Okay, in the field, but the sample was subjected to these stresses. Sigma value 240, pore water pressure was 140, and effective sigma is 10. Okay, so this was the stress state in the field. Now these are the various questions from A to H. Okay, that we need to calculate, that we need to find out. Okay, so the first is on sampling. What are the stresses acting on it? Okay, on sampling, what were the stresses acting? The sample was placed in a triaxial cell when was subjected to a cell pressure of 100 kilonewton per meter square under undrained condition. Okay, so this is asked to us. On sampling, what are the stresses acting on it? Okay, so okay, so this is the effective stress and this is the stress that is being encountered in the field. So what is the effective stress? The effective stress is nothing but the stresses that develop at a grain to grain contact. Okay, the stresses that develop due to the grain to grain contact. And then we are seeing telling that a sample was placed in a triaxial cell and was subjected to a cell pressure of 100 kN/m² under undamped condition. So now first condition is on sampling, what are the stresses acting on it? Okay, so right, on sampling sigma reduces to 0, right? Because you are taking out the sample, the sigma reduces to 0, but the sigma dash, that is my effective normal stress, remains unchanged. Okay, okay, this is because sampling was perfect and here change. So we have sigma equal to 0, meter square. So my total will be so my pore water pressure will be how much? Sorry, just a second. So pore water pressure will be minus 100, right? That's why this is 0. Now let us come to B. The B is what are the stresses? Okay, the sample was placed in a triaxial cell when subjected to a cell pressure of 100 under undrained condition. So now we have to tell what are the cells. So cell pressure of, we are applying a cell pressure of 100. That's good. So this will change to 100. U will be changing to minus 100 plus 100 equal to 0, and the sigma dash will be equal to 100. Okay. Then the cell pressure was raised to 320 kN/m² with the drainage valve closed. Okay, then we are again raising the cell pressure to 320. So as soon as we raise the cell pressure 320, the sigma will be low. Okay, U remains to 0 and sigma dash will be again to okay, the drainage valve was opened and the soil was allowed to consolidate under the cell pressure. Okay, now what we are doing after this, we are opening the drainage valve and the soil is allowed to consolidate under the cell pressure. What are the, again now you have to tell the values. So now after this stage, what we are doing is that we are allowing the drainage. So as we are allowing the drainage, what will happen? Water will drain out from the soil sample, and the water this water will start to drain out, right? The water will start to drain out. My, just a second, C, what was the C before the C? Yeah, this will be, I think, 3200, right? This is 320. Just a second, made some mistake here. See, before this it was that the cell pressure was raised to 320 with drainage valve closed. So we are just it is undrained condition, right? So up to 320 you are increasing the cell pressure. So what will happen is, so sigma will be equal to 320. Now the total stress will be equal to 320. Now now before this, so sigma will be equal to 320, and this is the undrained condition, right? So my sigma dash sig will be equal to 100 now, 100 kPa, and so this will be 200 kPa. Just a second, I will just check the values. Okay, 3 raised to 300, which means what? Celebration, then celebration is reached to 320 with drainage valve closed. By 220 by increasing. 220. Just a second. Okay, there might be some this in the solution. I think there is some problem in the solution is not correct, I guess. Cell pressure. Okay, so leave this question for now. I will see in the next class. Okay, I have to just check the solution once, because I think there is some problem in the values. That's why it's not matching. Okay, so leave this problem for now. We will discontinue this in the next class. Okay, I will just see this once properly, and then we will try to solve this one. This problem is actually a little typical, not that straightforward, and I think there is some problem in the solution also. Okay, so I will see this in the next class. So leave this one. Let us see the other problems. Okay, so you try, if you are able to solve this by yourself, just try once. I will check again with the solution this week, and I will see if this problem is fine, then I will try to solve it in the next class. Else you just leave this one. Okay, I did not see the solution before, so but now as when I am seeing the solution, I think that there might be some problem, so I am not sure. So let us not waste time in this, and let us go to the next problem. Okay. Okay, so UCS test was conducted on an undisturbed sample of clay. The sample had a dia of 37.5 mm and was 80 mm long. Okay, the dimensions of the sample are given. The load at failure measured by the proven ring was 28 newtons, and the axial deformation of the sample at failure was 13 mm. Okay, so we need to determine the UCS and the undrained shear strength of the clay. Okay, so you need to determine the UCS and the undrained shear strength. So sample diameter is given and the length of the sample is given. The load at failure is also given. Okay, axial deformation is given. So this failure load is given to us as 20 Newton. Okay, so what is the axial deformation? 13 mm, right? So what is my axial strain? 13 by 80. So what will be my area? 13 by 80, right? So let us calculate this. pi by 4 into 37.5 square 1 minus 13 by 80. Okay, be 1318.76 mm square. So this is my corrected area. Okay, this was my initial area. This divided by 1 minus here will give my corrected area, right? And I have my load. Now I need to determine my UCS. So UCS is nothing but this 28 divided by 1318.76. So it is nothing but 28 divided by 1318.76 is 0.0212 ton per mm square. So if this is the UCS, what will be my undrained shear strength? What will be undrained shear strength?
half the value.
Yeah, half the value. So Q by 2. Sorry, 0.0212 divided by 2. Check back to 0.010106 square. Okay, simple. Seventh problem we have in a CU test on a normally consolidated clay, the sample consolidated under a stress of 20 kPa failed at an additional axial stress of 150 kPa. Okay, in CU test on NC clay, the sample consolidated under a stress of 200 kPa failed at an additional axial stress of 150 kPa. The pore pressure at failure was 75 kPa. The pore pressure at failure was given to us. Determine analytically the shear strength parameters both in terms of effective and total stresses. What are the values of the principal stress ratios? That is both effective and this both effective and my total principal stress ratios. That is sigma 1 dash by sigma 3 dash and sigma 1 by sigma 3. Both of these things we need to determine, and also calculate the value of the A parameter at failure, AF it's written. Okay, so normally consolidated clay we are doing CU test. This was consolidated under a stress of 200 kPa. Okay, and this failed at an additional axial stress of 150 kPa, right? So determine analytically we need to determine. So first see, so what is given to us? What is sigma 3 at failure? What is sigma 3 at failure?
200.
200. What will be sigma 3 dash at failure? What will be sigma 3 dash? Just deduct the pore water pressure, right? 200.
minus 75.
Yeah, 200 minus 75. It is 125. What is sigma 1 at failure? What is sigma 1 at failure? What is sigma 1 at failure? Very easy.
200 plus 150, 350.
Yeah, 200 plus 150. It is 350 PA. And sigma 1 dash at failure will be 350 minus 75. That will be 275. Okay, so now we need to determine C5 and C dash 5 dash first. Okay, before that let us determine the principal stress ratios. What is sigma 1 by sigma 3 at failure? 350 divided by 200 dash at failure. This is 1.75. This is 2.2. Okay, Now my next part is to determine C phi and C dash phi dash. Okay. So how to determine these values? How to determine? Let us go to our basic equation. What was the basic equation? Sigma 1 is equal to sigma 3 then square 45 plus 5 by 2 2ic 10 45 plus 5 by 2. Right? Now, as this soil is NC, normally consolidated, so what will be my C values? What will be my C value here? It will be 0, right? We have studied that for normally consolidated clay, the C is 0, isn't it? The C is 0, right? For a is as the soil is normally consolidated, it can be assumed that my C dash and my C values are 0, undrained values and the C dash values both are 0, right? So it will be nothing but sigma 1 equal to sigma 3 by 2. Sigma 1 by sigma 3 you already know, you calculated just now 1.75. So please calculate 5 from here. Root over 1.75, then tan inverse of that, then minus 45 of that, then into 2, sorry, then into 2. It should be 15.8 degrees. Okay, and similarly we can find out this phi dash value, right? So you already know this 2.2. So please calculate the phi dash value. Root over 2.2 tan inverse of that minus 45 then into 2, 22 degrees. 22 degrees. Okay, so you can clearly see my phi dash is greater than phi in a normally consolidated soil, clay soil. Okay, phi dash is clearly greater than my phi. Now there is the second part of this problem. What was the second part? Calculate the value of AF. It is the value of my pore pressure parameter A at failure, right? Right. Just let me add one more page here. Sorry. Okay, A you need to find out. So what is A? If you can recall, what is A bar? What was the expression for A bar? Delta U by, right? So this was the expression. Now it is actually A bar is nothing but A into B. So as you can say, you can consider that the soil is completely saturated, so my B will be equal to 1, so my A bar is nothing but equal to A, so A is equal to 3, right? Now in the this is actually the delta u2, right? So now delta u is equal to delta u1 plus delta u2. So this delta u1 is actually equal to 0 because this is a consolidated undrained test. So in C first stage there is no development of pore water pressure. So this delta u is nothing but delta u2. So we can write delta u is equal to sigma 1 minus delta sigma 3. Now what is delta u now? Let us see. So what was the so we need to calculate it failure. Let us write failure. Failure. So how much the pore pressure increases? It is given in the question. The pore pressure at failure was 75 kPa, right? When was this 75 kPa? When this additional stress was 150 kPa, right? So due to this additional stress of 150 kPa, this 75 kPa pore water pressure is getting developed in the soil, isn't it? So what will it be? Nothing but 75 by 150, that is 0.5. 0.5. Okay, so this is within our range. We have started that for NC it should be between 0.5 and 1. So you can see it is coming within our range also. Okay, so I hope this was clear. Very simple. So main basic concept that you have to remember is that normally consolidated clay CU test, the C should be 0. Both C dash and C will be equal to 0. This is the first thing that should come to our mind. C should be by default should be equal to 0. Then what we have in our hand? We always have our this basic equation. This is our savior always, right? So we put C equal to 0 in both the cases, and sigma 1, sigma 3, sigma 1 dash, sigma 3 dash, we know. We put these values and find our phi and phi dash respectively. Okay. After this, it had been asked to us to find my A parameter at failure. So that is also very simple. Nothing but the change in pore pressure and that divided by the pore pressure that developed due to the increasing our axial stress. So that pore pressure divided by axial stress will nothing but the A parameter. Okay, so very easy, very conceptual and very easy also. Okay, so if this is clear, then let us go to the next problem. The results of a CU test on an undisturbed sample of an over consolidated clay were as below. Okay, so this is the result of a CU test that is given to us. Cell pressure is given, deviator stress at failure is given, and pore water pressure at failure is also given. We need to determine the effective shear strength parameters and plot the variation of my A parameter at failure with the over consolidation ratio. If the pre-consolidation stress is given, why the pre-consolidation stress is given to us? So that we can actually calculate the OCR. Okay, so the soil is actually pre-consolidated beforehand to a stress of 700 kPa, and after that we are reducing the stress and bringing out to first we are bringing the cell pressure to 100, then you are doing the test, then you are increasing to 200, then you are doing the test, 400 you are doing the test, and you are taking it to 600 and doing the test. Okay, so initially it has been increased to 700 pre-consolidated, then the cell pressure is reduced to 100 first, then 200, then 400, then 600. Okay, so we have to calculate the effective shear strength parameters and plot the variation of my A parameter with OCR. Okay, so let us first form our table. Okay, first column will be my test number, then it will be sigma 3 at failure, which is nothing but my cell pressure at failure. So my second column, then will be my deviator stress at failure. So what is my deviator stress at failure? Sigma 1 minus sigma 3. My deviator stress at failure, which is nothing but this. Then I can find out my sigma 1 at failure, right? Then I have my u at failure. From this I can find out my sigma 3 dash at failure and sigma 1 dash at failure, effective values, right? So this forms our table for a test. Okay, actually one more. Okay, now so okay, so I will make it later. So test 1, what is my sigma 3f? Please keep on telling me, okay, what is the sigma 3f for the first test? What is
100.
100?
100.
Then what is sigma df? 100, 300. Okay, so what will be sigma 1? 400. What will be, what is uf? It is given minus 45. So as you see it's minus, so this thing like this reinforces our thing that is over consolidated clay. Over consolidated initially it might be now when negative polar water pressure. Okay, and as the test progresses, our soil will tend to get closer to the pre-consolidation stage. It is if the see if sigma 3 crosses 700, if my sigma 3 crosses 700, my soil will become normally consolidated, right? So as the test is actually going near to 700 value, as the sigma 3 is going, see, as the sigma 3 is going near to 700 value, my pore water pressure is actually getting positive, right? It means is as the soil is getting transformed into a normally consolidated soil slowly. Okay, so this thing is happening. So let me write sigma 3 dash, what will be sigma 3 dash? 100 minus 45. 100 minus 45. What will be sigma 3f? Please tell me what will be sigma 3f dash?
145.
145. And what is sigma 1 dash? 445. Test 2 again we have 200, 410, 610 minus 15. So 200 plus 15, 215 is 625. Right. Test 3, 400, then 610, then 1010, then 50. This is positive now. So 400 minus 50, it will be 350. 960. Then we have 4 test. This sigma d 600, sigma d 850, will be 1450. It will be 110, 490, 1340. Okay, so we got this. Now what we can do, we need to determine the effective shear strength parameter. So we will be, what we will be doing, we will be using we will be using these two columns to plot our more circles and to determine our effective shear strength parameters. Okay, so as we plot the more circles, you can see these are the more circles that were plotted. Okay, so for 4 tests we have this first 1 2 3 4, 4 more circles are plotted, right? 4 more circles are plotted. So initially this was, see, this was 145, this is 445, this is 215, this is 625, like this all the 4 circles are plotted. After plotting this more circle, what we are doing, we are drawing a straight line, a common tangent to all these circles, that will give us the, what is this? This is nothing but a failure envelope, right? And the slope of the failure envelope we can find out after drawing. So we are getting phi dash equal to 25 degrees and C is coming out as 30 kPa, right? So next part is we need to plot the variation of AF with the over consolidation ratio. Okay, this is my next part. So now let me make another table. Here we have sigma 3, we have over consolidation ratio, we have F. Okay, so first my sigma 3 is 100. So what will be my over consolidation ratio, over consolidation ratio for OCR or OCR when sigma 3 is 100? What is over consolidation ratio? pre-consolidation stress divided by the present stress, right? So what is my pre-consolidation stress? It's given in the question 700.
700.
So 700 divided by 100, so 7 OCR. Then again we have 200, so 700 by 200, nothing but 3.5. Then we have, this is 400, so 700 by 400, 1.75. Then we have last was 600, so 700 by 600, 1.2. So if this OCR is equal to 1, that means normally consolidated soil. So it is slightly less than 1, right? It is 600. Now what is AF? AF is nothing but this delta U by delta sigma D, right? So what is, for the first case, what is my sigma, say this pore water pressure, minus 45. So minus 45 by the weight of stress, minus 45 by 300, right? So minus 45 by 300 equal to minus 0.15. Then next case, minus 15 divided by 410, that is 0.036, 0.037. Then 50 divided by 610, then 110 divided by 850. So 50 divided by 610 is 0.082, and this last one will be 0.13. Okay, so this one we got. Now we have to plot this. So let us draw. Okay, so this side we have the OCR, this side plus AF, this side minus AF. Okay, so when the OCR is here, see, we will be getting a line like almost like this. So say it's 1 2 like this, right? 2 7, say. So you will be getting a line like this. So initially OCR was high, my AF was negative 0 2. Okay, it was negative. Then what we are doing, as the OCR reduces, it is tending to it is becoming almost positive. Okay, it is tending towards positive. So this will be the variation of my AF with the OCR. Okay, that is the over consolidation ratio. So normally consolidated, we know that A is always positive. So as the soil is tending towards the normally consolidated state, we are getting a value that is greater than 0. Okay, we are getting a value greater than 0. So if the soil would have been completely normally consolidated, we would have got a value that is between 0 and 0.5 and 1. Okay. So at this point we are getting what? A value are we getting here? We are getting 0.13 here, A value 0.13, right? It is 0.13. So it is neither over consolidated, completely over consolidated, neither not completely normally consolidated. So it is something in between. So for NC, A value is always between 0.5 and 1, and for OC it's between minus 0.5 and 0. Okay. So this is our case. Now let us move to the next problem. A compacted soil was tested in an undrained triaxial test using a cell pressure of 400 kPa. Before the application of cell pressure, the pore water pressure in the sample was 0. Okay, so before the application, the pore water pressure is 0. Undrained triaxial, undrained test, right? So these are the values given. The strain is given, deviator stress is given, and pore water pressure is given to us. Okay, so you can see that when my deviator stress is 0, a certain amount of pore water pressure is there, which is nothing but 250 pore water pressure is there. So can you tell me from where is this 250 coming? This 250 is from, how this 250 got developed? You are not applying deviator stress, right? So this is not from the deviatoric, not due to the application of deviatoric stress, right? So what is the other stress that you are applying? Cell pressure. So this 250 pore water pressure that is getting developed at a deviator stress of 0, obviously this must be developed due to the cell pressure, right? This is not getting developed due to the deviatoric stress. This is coming from the cell pressure. So when as you are applying 400 cell pressure, the pore water pressure is developed is 250. So first question is, was the soil completely saturated? Can you answer this? Was the soil completely saturated? Please look at the question properly. We are applying a cell pressure of 450, and against that 450 the pore water pressure that gets developed is 250. Sorry, we are applying 400, and against that pore water pressure that gets developed is 250. So is my soil completely saturated? Is my soil completely saturated?
Question still difficult to understand.
See, we are applying cell pressure of 400 kPa, right? Due to the application of 400 kPa cell pressure, we are getting a pore water pressure that is generated in the soil that is equal to 250 kPa. We are applying 400 kPa cell pressure, okay? So this is a sample. We are applying all round cell pressure, right? Okay, so due to this so we are applying all around 400 kPa cell pressure. Due to this all around, so this is the sample. I am applying all around 400 kPa cell pressure. Okay, so due to this application of all around 400 kPa, the pore water pressure that is getting generated in the sample. Okay, as I am applying some stress, my sample is undrained. We are not allowing drainage. So water is there in the pore, right? Water is there. Soil is undrained test. As soon as I'm applying some stress, external cell pressure, some pore water pressure will get generated, right? That pore water pressure is given as 250. You are applying 400 cell pressure, you are getting 250 pore water pressure. So is my soil completely saturated? Can you tell me from this data? So what, first let us determine this B. What will be this B parameter? What is B parameter?
Delta U by
Delta sigma 3.
delta. Yes.
So what is delta sigma 3? Delta sigma 3 is 400. So due to this 400 application, what is the pore water pressure that is getting developed? 250.
It's not completely saturated.
Yeah, not combined because it is less than 1.
Less than 1.
Right? Is that what? If it would have been completely saturated and I would have applied 400 kPa cell pressure, I would have got pore water pressure is equal to 400 only. Okay. Whatever cell pressure I would have applied, the same increase. Say I would have applied 200 cell pressure, I would have got pore water pressure 200. Okay, so we can tell that the soil is not saturated from this because my B is less than 1. Next, it's asked to plot the deviator stress with strain. So if you plot the deviator stress, so it's, see, you cannot plot it now, right? So if you plot the deviator stress with strain, we will get a curve like this. Okay, this is sigma 1 minus sigma 3. This is strain percentage. Okay, we'll get some curve like this. You can draw this by yourself in Excel and check once. You will get one curve like this. Okay. Okay. So plot and check once. Okay, in Excel, please plot and check how what type of curve you are getting. So for the previous one also, please plot and check by yourself in Excel once. Okay, what kind of curve you are getting. Now second is plot. We need to plot A with strain. We need to plot the A parameter with strain. For that we need to find the A parameter, right? So let us make a table. I will just erase it to make some space. So strain, okay, strain, then delta U2, delta sigma 1, delta sigma 3, then we have A dash. A dash is, what is A dash? Tell me, what is the value of A dash?
AB.
No, yeah, correct, AB. Well, correct, we'll write it in the next part. So A dash is AB, so what will be A? We are asked the question, we are asked about A, right? So here B is not equal to 1. So A dash won't be equal to A. So A will be equal to A dash by B. Right? So A dash by 0 point how much? This is how much? 250 by 400? 0 0.625. 0 0.625. Okay. So we have strain. So first strain was 2.5%. It was given. So we are writing from here. Okay. From here. 2.5. My pore water pressure was 285. Right. So what is the increase in pore water pressure? From 250 to 285 by 35. Right. So it's getting increased by 35. What is delta sigma 1 minus this deviator stress test? You write down deviator stress here. Okay. Like this, as you need to fill it. Next is 5. What is delta U2? It is reducing. See, from 285, the pore water pressure reduces to 150. So 150 minus 285. It will be minus, sorry, 250 to 150. So from 250, it's getting reduced to 150. So it will be minus 100. Minus 100. Okay. And this one was 950. Like this, for 7.5 we have 250 to 105, so 145 minus 145, this is 1100, it's given. Then 250 to 75 we have minus 175 for 10, 50. Then same for 12.5 we have minus 190. Okay. Okay. So these are the changes in deviatoric stresses, and these are my delta sigma 2. Okay. This is delta sigma d, right? So initial delta sigma d was 0. So from 0 we are deducting everything. All that differences we are taking. 0 minus 750, 570 minus 0 is 570, 950 minus 0 is 950. So like this we are doing. And these are the increase. Remember, these are the absolute value, total values, and from 250 you are deducting this from 250. 250 this minus 250, you are getting the change. Okay, change in pore water pressure. So what is A dash? So thus this divided by this, 35 divided by 570, 0.061, then it will be minus 0.105 minus 0.132. Okay. So this divided by 0.625, 0.061 divided by 0.625 is 0.097. So very simple, just divide by 0.625. Okay. So again, if you plot this with respect to strain, you will get some graph like this. Okay, just plot and check once. Just plot the A values with strain. So here you take strain here and here A values, just plot. You will get some graph like this. Okay. Okay. So yeah. So this problem, in a triaxial test, a soil sample was consolidated under a cell pressure of 700 kPa and a back pressure of 350 kPa. Thereafter, with drainage not allowed, the cell pressure was raised to 800 kPa, resulting in the increasing pore water pressure of 445. The axial load was increased to a deviator stress of 575, and the cell pressure remained 800, and pore pressure. Calculate the pore pressure coefficients A and B. Okay, so first we need to calculate the pore pressure. Calculate the let us calculate the B parameter first. So what is B parameter? Right. So the cell pressure is increased from 700 to 800. Okay, due to this increase in cell pressure, okay, what is the increasing? So see, initially cell pressure was 700 and back pressure was 350, means back pressure was actually back pressure is actually equal to the pore water pressure here. Okay, back pressure is actually equal to the pore water pressure. Okay, so back pressure is equal to the pore water pressure. So at 700 my pore water pressure was this much, 350. Okay, and when the cell pressure was raised to 800, the pore water pressure, that is the back pressure, increased to 445. So what?
445 minus 350 by
350, 50 divided by this sigma 3, change in sigma 3, it is 800 minus 700, this will be 0.95. So almost solely saturated, so close to 1, right? Now next part is we need to determine the a value. So in increasing the total measured principal stress from 800, see initially it was 800, so from 800 it was increased to 800 plus 575. Okay, so initially sigma 1 was equal to sigma 3 equal to 800, then sigma 1 became sigma 3 plus 575, that is sigma d. Okay, that is whatever 800 plus 575, you what is that, 800 plus 575, 1375. So initially my sigma 1 was 800 and then my sigma 1 change to 1375. So 5, so this by 575 this is increasing, so this is my increasing my deviatoric stress, right? So what is a dash is delta u2 by sigma t. So delta u2 is 640 minus 445, right? So 445 was the what, 445 was the pore pressure at the end of my consolidation state, right? As I increase the cell pressure to 800, my pore pressure reading was 445. Then what I did, then I started applying my deviatory stress, and I started applying, and then my deviatory, when my deviatory stress was 475, my pore pressure was 640. So 640 minus 445, this much is the increase in the pore pressure due to the application of my deviatory stress. Right, so this much pore pressure is increasing due to the application of this much deviatoric stress. So this divided by 575. This will be actually 0.339. So if this, so you got a value, a dash value, so a will be nothing but a dash by b, 2.339 divided by 0.95 will be 0.357. Okay, so I hope this is clear. So first b parameter you have to find out. B is the ratio of the increase in pore water pressure due to the cell pressure divided by the increase in cell pressure. So due to the increase in my cell pressure from 700 to 800, my pore water pressure got increased from 850 to 445. Okay, so using this is the first part. Okay, from this I found out my b. The second part is that where due to the increase in deviatoric stress from 0 to 575, due to the increasing deviatoric stress from 0 to 575, my pore water pressure is changing from 445 to 575, right? So 6 what sorry, from c where is it, yeah, here. So pore water, final pore pressure is 640. So due to the application of this 575, my pore pressure increased from 445 to 640. So 640 minus 445 divided by the increasing my deviatoric stress. This is 575. That will give me the a bar. Right. So a bar we got. Then we can find out a is equal to a bar by b. Okay. Quite simple. So just we have to read the question very clearly, okay, very carefully what is happening there. So first is the consolidation state, only cell pressure is applied. So cell pressure increased from 700 to 800. Due to this, my pore pressure increased from 350 to 445. Using this, I got my B value. Second is my A comes my deviatrix state. So deviatrix state, due to the increasing deviatrix stress from 0 to 575, my pore pressure got increased from 445 to 640. So using that, I got my A pathway. Okay. Okay, so I have one more problem, last problem. So this is also based on this U test only. So cell pressure is given, same deviatory stress at failure is given, and pore water pressure at failure is given. Okay, so this sigma 3 I know, sigma D I know. I can get sigma 1, I can get sigma 3 dash, I can set sigma 1 dash, I can get P dash, I can get Q dash, right? I can get P dash, I can get Q dash. Okay, so let us see what is sigma 3 first, 150. What is sigma D? 102. What is sigma 1? 2. Right. What is U? 80. So sigma 3 102 minus 80. So I will just write the values fast. Okay, it's just nothing but addition and subtraction, nothing else. So 70, 72. So what is P dash? P dash is nothing but Q1 dash plus Q3 dash by 2. And what is Q dash? Sigma 1 dash minus sigma 3 dash by 2. We will just do this addition and subtraction, divide by 2, get the 21. Okay, similarly for 300 we have 200, we have 500, we have 164, 136, 336, 100, 36. Okay, then 450, 304, 754, 246, 204, 508, 152, 356. Then we have 600, 405, 1005, 55, 275, 680, 203, and 470. Okay, we got these values. So using this sigma 3 dash and sigma 1 dash, you can plot the mode circle, effective mode circle. We'll get our failure envelope will get, and from there we can get my C. From here we will receive C dash, and phi dash we can get. Now similarly, what we can do is that we know the P dash and Q dash. So what we can do, we can draw our KF line, P dash and Q dash. So if we draw this all the points, we will get a straight line. This will give you your, so before I get written this at alpha, so I will again write it as alpha only, alpha value. Okay, so this alpha value you will get it as 23 degrees. Now you had one relation between alpha and phi, right? What was the relation? Phi dash is equal to sine inverse tan alpha. Okay, so you put 23 degrees here, you will get 25.5. okay, you will get approximately 25 degrees, right? So in the same way, what you can do is that you can also determine the total stress parameters by plotting P and Q. You can also plot P and Q, and from there you can get phi value. And one more thing I wanted to tell you that say this P and Q, when you are plotting this P dash and Q dash, say you get some intercept A, this is alpha, say you get one intercept A here. So from A, how can you determine the cohesion? You can determine the cohesion by using this relation, by cos phi. So first what you do, first you determine phi is equal to sine inverse tan alpha, and then after determining phi, determine C is equal to A by cos phi. A is nothing but the intercept made by the kf line in the p dash q dash space. Okay, like this you can find out. Similarly, you can do it for you can find the total stress parameters also by plotting the pq. In the pq space, if you plot the kf, and you will get the total stress parameters. Okay. Okay, so that's all. With this, we will end today's discussion. And that one problem which was left, I will see if it's possible. I will do it in the next class. I will just have to see that problem once. Okay, recheck that problem once, and if that's correct, then we will be discussing that in the next class. And also, in the next two classes, we will be solving several problems on the earth pressure theories, active earth pressure, passive earth pressure, all those things. That is also very interesting. We will be solving those problems, uh, and then in the last class we will be summarizing the last discussion. In the 12th week we will be summarizing everything whatever you have studied from the first chapter to the last chapter. Okay, so with this we will end. If there is any doubt, I hope like you can ask me anytime about any problem. So I hope everything was clear. Okay. So
Yes, sir.
thank you for attending. Okay, thank you. Good night.